We shall continue our discussion on the application of the theory of small oscillation as applied to system having 2 degrees of freedom. That is, we consider two linear oscillators coupled together. Earlier we have worked out in detail two such examples and outlined few more. In all of these examples, the oscillators were coupled via stiffness, that is the force that acts between the force that acts on the oscillator 1 due to 2 depends on the relative separation between the two oscillators, that is to say, as if the oscillators were connected via elastic springs. And when we cited few examples of identification of Lagrange kinetic and potential energy matrices for when the Lagrangian is supplied, then we have discussed few cases where the we have encountered oscillators which were coupled inertial. Here we shall consider a system of two oscillators which are inertially coupled oscillators. Namely, we shall consider the double pendulum case. Two inertially coupled oscillators. The situation is like this: we have a fixed support, we have a string of length L1, and we have a mass bob of mass M1, and we have another string of length L2, another string of length L2, and a mass M2. The diffraction from the horizontals are denoted by θ1 and θ2. These are the generalized coordinates. Generalized coordinates for the system, and we consider this coordinate system like this. This is x-axis, this is y-axis. So if we write the position of the mass 1 to be x1, y1, and that of 2 is x2, y2, then clearly x1 is equal to L1 sin θ1 and y1 is L1 cos θ1. Similarly, x2 is equal to x1 times L2 sin θ2, which comes out to be L1 sin θ1 plus L2 sin θ2, and y2 is equal to y1 plus L2 cos θ2. So this is L1 cos θ1 plus L2 cos θ2. Now coming to the kinetic energy. Kinetic energy is half m1 x1 dot square plus y1 dot square plus half m2 x2 dot square plus y2 dot square. If we find our x dot, x1 dot, this is half m1. For x1 dot, it is L1 cos θ1 dot plus this is minus L1 sin θ1 dot square. And for this part we have half m2 if we differentiate x1, this is L1 cos theta 1, L1 cos theta 1 dot plus L2 cos theta 2 dot, this whole square, and for y2 part there will be two negative signs, so we write it minus L1 sin theta 1 dot minus L2 sin theta 2 dot square. If we simplify, this is half m1 L1 square theta 1 dot, this is m1 L1 square theta 1 dot square, and if we come to this part, this is half m2. This part leads to L1 square theta 1 dot square, because square terms, this L1 square cos square theta 1 plus L1 square sin square theta 1 leads to this, and similarly we have L2 square theta 2 dot square, and then we have the cross term. The cross term is twice L1 L2 theta 1 dot theta 2 dot, and this is cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. So we write it as half m1 plus m2 L1 square theta 1 square dot square plus half m2 L2 square theta 2 dot square, and coming to this term. This term is basically cos of theta 1 minus theta 2. This is cos of theta 1 minus theta 2. Here we assume that these angles are nearly equal. This is an approximation. We assume that the angles are nearly equal so that this part may be approximated to be 1. Otherwise, if we retain this term, the calculation becomes extremely complicated. So to get rid of complicacy, we write it like this, and so that this term is m2, sorry, this term is m2 L1 L2 theta 1 dot theta 2 dot, and there is an approximation. So the T matrix, so to say, the T matrix becomes m1 plus m2 L1 square. This is the 2 term is m2 L2 square, and this term is m2 L1 L2 m2 L1 L2. If we look at the T kinetic energy part, this is the coupling term, and the coupling is coupling here appears as the product of velocities. So this is the T matrix, and the V matrix. So let me write the T matrix for the system is m1 plus m2 L1 square m2 L1 L2 m2 L1 L2 m2 L2 square. Now coming to the potential energy. The potential energy is, if we take, this is the zero level of gravitational potential, so if we consider y is equal to 0 as the zero level of the gravitational potential, the potential energy is minus m1 gy1 minus m2 gy2. So we have assumed v to be 0 at y is equal to 0. This is minus m1 plus m2 gy1 minus m2 gy, sorry, m2g for y1 we write L1 cos theta 1, and this is minus L2g L2 cos theta 2. Now we approximate it by expanding cos theta in Taylor series. This is 1 minus theta 1 square by 2, so there is an approximation, and for this it is minus m2g L2 1 minus theta 2 square by 2. Now we have to find out the matrix element of V. We know that we define P1 is equal to del V del theta 1. So this minus makes the sign plus m1 plus m2 gl1 theta 1 dot. Sorry, theta 1. And P11 is the del 2V del theta 1 2. So this is when we differentiate it, we get it as m1 plus m2 gl1. In the other case, there were no constant term in the potential. Here we have a constant term m1 plus m2 gl1, and m2 gl2 is the constant term. We may say that we ignore the constant term, and then we can all again reconstruct the V matrix, but the easier way of constructing the V matrix is through this expression. So now coming to V2. V2 is del V del theta 2, which is coming from this m2 gl2 theta 2, so that V22 is equal to del 2V del theta 2 which is m2 gl2, and the cross term, that is P12 is equal to del 2V del theta 1 del theta 2. This is 0, and so is the V21. So the V matrix is a diagonal one, and this is V1 as M1, M2, GL1, 0, 0, M2, GL2. We may carry on our calculation with such M1, M2, L1, L2, but as we shall see afterwards, the algebra involved becomes becomes very complicated. To simplify algebraic manipulation, or to simplify mathematics involved, we make an approximation, that is, to simplify mathematics, mathematical manipulation or mathematical steps. we write L1 is equal to L2 is equal to L, and M1 is equal to M2 is equal to M. That is, we consider two identical units of simple oscillators, one connected at the end of the other. In which case, the T matrix becomes, this is twice ml squared, and we can take ml squared common, to 1, 1, 1. And the V matrix becomes twice GL, and if we take ml square common from it also, so this is twice G by L, 0, 0, G by L. So these are the T and V matrices. Note that we have taken ml square common from both these two, which will drastically simplify our calculation. Eigenvalues, eigenfrequencies. Eigenfrequencies are obtained from the secular determinant, that is det of V minus omega square T is equal to 0, which in this case becomes, we need not to consider ml square. So this is, here it is 2, here it is 2, so we take 2 common, G by L omega square, and this is minus omega square, and this is G by L minus omega square is equal to 0. So that we have twice G by L minus omega square is equal to omega to the power 4, or root 2 G by L minus omega square is equal to plus minus omega square, or omega square is equal to, or on simplification we get omega square is equal to 2 plus minus root 2 G by L. We call omega 1 square is equal to 2 plus root 2 G by L, and omega 2 square is equal to 2 minus root 2 G by L. These are the two eigenfrequencies. Now what will be the eigenvalue equation? So if we want to find out eigenvectors, the eigenvector will be obtained from this relation, that is 2 G by L minus omega I square minus omega I square, and this is G by L minus omega I square. This is for the eigenvalue problem, A1I, A2I is equal to 0. This is the equation which allows us to find out the eigenvectors. So we write for omega 1 square is equal to 2 plus root 2 G by L. We see that G by L term will be everywhere, so we need not to worry about G by L term. So we have, in this case, 2 with outside, this is 1 minus this, 1 minus 2 minus root 2. This is 1 minus omega square minus omega square. So this is 2 plus root 2, and this is minus, and in this case we have 1 minus 2 root 2 a11 a21 is equal to 0. Or if we look at it carefully, this is minus 2 1 plus root 2. This is minus 2 plus root 2. This is and this one is, if we take minus 1 common, 1 plus root 2. Or we have minus 2 1 plus root 2 a11 minus a21 is equal to 0. So if we take root 2 common out of it, we get 2 1 plus root 2 a11 is equal to minus, taking root 2 common, 1 plus root 2 a21. So this part goes, so we have root 2 a11 is equal to minus a21. Let us call a11 is equal to alpha, then a21 is minus root 2 alpha. Now the task is to find out the alpha. Our task is to find out alpha. The normalization constant condition for the T matrix is that summation over ij a1 r Trij aj1 is equal to 1. Here I and j runs from 1 and 2. So we have a11 square t11 plus a21 square at1 square t22 plus there will be 2 cross terms, 2 a11 a21 t12 is equal to 1. Now coming to the T matrix. T matrix is ml square common, or ml square common, t11 is then 2 and this is alpha square. For this it is 1 and t12 is root minus root 2 alpha, so this is plus 2 alpha square, and for this it is t12 is 1 and this is minus 2 root 2 alpha square is equal to 1. So we have 2 taking out common, 2 ml square alpha square is equal to 2 minus root 2 is equal to 1, or we have alpha is equal to 1 upon 2 ml square 2 minus root 2 and backward. So altogether what we get, the matrix for omega is equal to omega 1, we get the eigenvector like this. The eigenvector is A1 eigenvector is equal to A11, A21, which when alpha taken common 1 minus root 2. So this is, and the value of alpha is this 2ml squared 2 minus root 2 1 minus root 2. This is the first eigenvector. So so let me write the first eigenvector. So first eigenvector is A1 2ml square 2 minus root 2 1 minus root 2. And similarly, we can carry on calculation for the determination of the second eigenvector. Second eigenvector, this part is alpha, and the second eigenvector will be 1 upon 2ml square 2 plus root 2, and if we carry out calculation, it is plus root 2. We call it alpha, as we have called earlier. This is equal to alpha, and this part we call it as beta. So we have solved the problem for the determination of eigenvalues, eigenfrequencies, and eigenvectors. So this is another goal. This is A1 is alpha times 1 minus root 2, and this is beta times 1 plus root 2. So what is the displacement? Eta 1. Eta 1 as a function of t is A11 C1 e to the power I omega 1 t plus A21 C2 e to the power I omega 2 t. Now, this is equal to alpha taking common C1 e to the power I omega 1 t plus C2 e to the power I omega 2 t, and eta 2 is equal to A12 C1 e to the power I omega 1 t, A22 C2 e to the power I omega 2 t, and these are this comes in terms of beta, so C1 sorry, I have made a mistake. This should be minus root 2, and this should be plus 2, because A11 is alpha and A21 is minus root 2 alpha. So alpha is taken common, so these are the displacements. So eta 1 is equal to alpha taken common C1 e to the power I omega 1 t minus root 2 C2 e to the power I omega 2 t, and eta 2 omega 1 t plus now, to find out the normal coordinates, we have to construct the modal matrix. The modal matrix A, the matrix, modal matrix A is A11, A12, A21, A22. So this is alpha minus root 2 alpha beta plus root 2 beta. The determinant of it is 2 root 2 alpha beta. Now the transpose matrix, cofactor matrix is root 2 beta. For this element it is alpha. For this element it is root 2 alpha, and this is minus beta. So AC transpose so A inverse is 1 upon beta A times cofactor transpose. So this is 1 upon 2 root 2 alpha beta, then root 2 beta, root 2 alpha minus beta plus alpha, which is 1 upon 2 alpha beta, 1 upon twice alpha beta, then this is beta alpha minus beta upon root 2 alpha upon root 2. So we know the normal coordinates. Normal coordinates are obtained from this matrix relation, that is xi ket is A inverse beta 1 ket. So we have xi 1 of t is equal to 1 upon twice alpha beta, this multiplied by beta multiplied by beta 1 minus beta by root 2 multiplied by beta 2. So this is 1 upon 2 alpha beta 1 minus 1 by root 2 beta 2, and similarly xi 2 of t 1 upon alpha beta, this is alpha times theta 1 plus 1 by root 2 alpha times eta 2, which is 1 by beta, beta 1 plus 1 by root 2 beta 2. These are the two normal coordinates. One thing I have forgot to mention, that the significance of the sign. By this time you are aware of the fact that this is out of phase oscillation, this is in phase oscillation, and the displacements are not of equal magnitude by equal amount, but there is a factor, root 2 factor involved in between them. So that's all about our example on inertia coupled oscillator. So this is the double pendulum problem. In the next class we shall consider an example where we have a system of 3 degrees of freedom and their stiffness coupled, namely we shall consider a linear triatomic molecule.